If you've been following computer displays, you've probably heard of a lot of terms getting tossed around. CRTs versus LCDs versus LEDs versus OLEDs. But what exactly are these display technologies and how do they differ? How do they work and which ones should you consider? In this video, I'm going to try to explain the fundamental differences between the three main categories of displays.
Hello, and welcome to Monitors 101. This is a quick video series I'm doing that talks about the basics of display technologies. This series will take you all the way from the beginning with CRTs all the way up to the most recent developments with OLEDs and micro-LED displays. The main video is linked in the description down below, but because it's an hour long, I thought I'd also make this three-part version, which kind of splits up into more manageable chunks. Part 1, which is the video you're watching right now, talks about the fundamentals, including CRTs versus LCDs, as well as the basics of how displays and monitors effectively work. Part 2 and Part 3 are linked in the description down below. Part 2 talks about types of LCDs, including VA versus IPS versus TN panels, as well as the different backlighting types you'll see, including CCFL, LED, as well as Mini LED. And Part 3 will talk about the latest and greatest OLED as well as self-emissive micro-LED panels, as well as the benefits and the drawbacks of using self-emissive display technologies. Without further ado, here's Part 1.
Over the last 30 years, the three most common types of displays have historically been CRTs, and those are cathode ray tubes. And then those were dominant all the way from the invention of computers and television all the way until the 2000s. In the 2000s, we started to see LCDs, LCD being liquid crystal displays. And more modernly, in the past 5 years, we've seen the introduction of newer self-emissive panels. These include things like OLED and micro-LED, with OLED being the current dominant type in that category. So, as I said, of these, everything before the 2000s was pretty much all CRTs. Most of the LCDs, now we're moving on to OLEDs. But within each of these, we also have lots of various categories. You've probably heard terms like IPS, VA, or TN getting tossed around. Those are all various subtypes of LCDs, and we'll explain these in a little bit more detail. Now, each of these can be defined by two main properties. First of all is how they fundamentally work and whether they are self-emissive. And we'll start from the old, progress onto the new, and then we'll also talk about what each of those subtypes mean and how they impact the output. Starting with a typical CRT, I'm not going to spend as much time on these because you don't really see them around well at all these days. But for a typical CRT, you would have an electron gun shooting in a vacuum tube to the display. The display would then be coated with various phosphors. Traditionally, these panels were curved, if you look at older TVs, just because so it had the same duration or the same distance to the middle as well as to the sides for when the gun is scanning. And how these worked was essentially you would have two coils, one doing your XY and one doing the one doing the x-axis, one doing the y-axis. And since electrons are negatively charged, you can always use electromagnets to shift the beam. So essentially, on your display, if this is so looking at it from the front, whereas this would be a side view. If you're looking from the front, without any input to those electromagnets, you would just get a dot in the middle. And of course, we then use electromagnets to scan all the way here from left to right, as well as top to down, ending the frame here. And of course, then that shoots back up. We can, there's lots of different characteristics here. For example, you use essentially, CRTs make use of flyback transformers in order to convert an incoming sine wave input into a square wave so that that looks something like this. And that's what allows the axis to go left to right and then immediately shoot back left in time to draw the next row, whereas you see the same thing happening from top to bottom. So it'll go top to bottom when it's ramping up and then immediately shoot back to the top. And of course, this means that the display has to be mounted at a slight angle because otherwise, as you might imagine, if the down display is always, so if this is, say, the y-axis, the x-axis is, of course, going to be a lot slower and then eventually reach up there. So if this is the x, the horizontal is a lot quicker because you scan left to right first, and that happens for however many lines you have, and then you'll have to go bottom to top. So you would notice that then there is essentially a large vector that moves this way, as well as a small vector that's pointing you down, which would result in a diagonal line. So instead, we tilt the display slightly so that the added vector will go straight. But that's basically nitpicking into fine details at this point, and those don't really impact the experience too much. The core thing is we will using a single phosphor, you would get a black and white output. To get color output, we started using multiple phosphors, and that's how we have data volts, RGB phosphors to do for television as well as computer monitors. And CRTs reigned supreme until roughly the 2000s. They have some of the benefits that you would get with a modern technology like OLED. Fundamentally, so while the X and Y is influenced by the electromagnets, the actual brightness of the dot, how bright of that point in the screen is going to be, is determined by how much power you're sending to the electron gun. So if the screen is supposed to be black, you're not sending any power at all, which means you will actually get near a pitch black output, which you don't get with LCDs, and we'll talk about why. So typically, great in the dark because you have very good near black levels when the electron gun is shut off, as well as you have pretty much no motion blur. Well, you have a bit of blur because that's what's needed to work. Essentially, the whole way where CRTs work is through persistence of vision, which means that you're just relying on the fact that after this thing scans by, the human eye just happens to see those pixels as still glowing, even though, well, the electron gun's no longer pointed there. So we rely on this, the phosphors to maintain the output for slightly longer so that essentially after an electron hits them, they'll kind of do something like this where they'll ramp down slowly, and then you rely on the brain to smooth that out over a frame rate. But this means that you practically get zero motion blur because the whole frame is being properly redrawn. And well, for 99% of the time, each pixel individually itself is pretty much dark. It only lights up, well, when the electron gun points to it. So although this was essentially improved over the years to have flat displays, and then Sony has their Trinitron tubes, which use aperture lines in order to get a much cleaner image, fundamentally this has remained the same. And you also probably heard that these run entirely analog, and there's really no such thing as pixels. If you zoom in if you look in with a magnifier glass, you will see RGB, what look like subpixels. That's actually part of a shadow mask. So that means that at non-native resolutions, the image will look pretty sharp because, well, there is no set defined line of pixels that would exist on something like a modern display. So unfortunately, though, mercury, lead, and shooting electrons turns out to not be the best idea, particularly for when you need to get rid of these things, as well as having fundamental issues like burn-in. Burn-in, which we will get back into when we talk about OLEDs and more modern technologies. Because essentially, if the image is always pointing at the same spot for too long of a time, that area of those phosphors will start to wear down because of constantly being bombarded by these electrons. And that means that you will always be able to view, like, essentially a preview of that image. You'll see this particularly with CRTs hooked up to like CCTV cameras, where the image will be completely burned in because of a static, non-moving thing. Or like a TV showing the news, the logos will be completely burned. So that's CRT. So they're roughly self-emissive. They contain toxic chemicals. I mean, we no longer use them. The most common type we use these days are LCDs. With LCDs, again, we'll do a side view first. LCDs themselves, as the name implies, it's liquid crystals. Essentially, it's a gel-like substance. And depending on the type of LCD you're using, LCDs can be very simple. If you look at any basic calculator with a 7-segment display, chances are the 7-segment display is using an LCD, not an LED. You can tell because if you tilt it, you'll be able to see at various angles how it looks. Also, if you take a polarizing filter and you rotate a polarizing filter, you'll be able to find angles where you can and can't make up the image, which says a lot about how they work, but we'll get back to that. And how they work depends quite a bit on the type of LCD. So again, a basic LCD would be something like you see in a calculator. And of course, as with OLEDs, there's passive-driven, passive matrix, as well as active matrix LCDs. Pretty much, I think most things are active now. So TFT LCDs are thin film transistors. So that's basically where, I mean, exactly as the name implies, you have a thin film of transistors, and you are actively driving the full display. Actively means you're providing a signal the whole time to each individual pixel. But essentially, if we look at it from the front, as you might expect, let's assume that this is a much lower, very greatly zoomed in. So assume on a black and white LCD, these pixels will typically be square. On RGB LCDs, they're typically rectangles. We'll talk about why. But essentially, each one of these will be able to be a 1 or a 0, or on modern displays out. I mean, for something like a calculator, it'll be a 1 or 0, either black or white, essentially. But for modern displays, we can do 8-bit, 10-bit, basically shades of how emissive they're going to be. Well, not emissive, but how transparent or opaque. And we'll talk about why that matters. But on a modern display, you'll probably get RGB stripes. And the pixels will be rectangular typically, or each subpixel will be. And that will just be to ensure that when you look at a pixel as a whole, it's roughly square. I mean, it will be perfectly one-to-one square on computer monitors. Computers use square pixels. But you will divide that into 3 thinner rectangles so that it results in a complete square. Now, the important thing is if you look at one of these from the side, obviously they're quite a bit more popular than CRTs, even when they first came out, because it's a lot thinner, it's a lot lighter, much thinner, flat screen lighter. You can actually put it on laptops and whatnot, which would have been impossible with big fat CRT tubes. And of course, CRTs limited how big you could make a display because you needed space in all 3 dimensions to fit the massive electron gun and vacuum chamber now. So much easier in that regard. We have a flat screen. Each pixel itself, as I said, is pretty much gets to choose between whether it is opaque or transparent. So if we look at one individual pixel, that pixel can be, well, pixels are typically circular, unless you're talking about OLEDs, they're typically square. The gel substance can go between being, well, it actually doesn't go between being transparent and opaque. What you can actually do is, for example, I'll use TN as an example because it's one of the, well, at least by today's standards, one of the simpler types. IPS and what Samsung used to call PLS work in similar manners, but slightly different. So we will get to the types of these later on. And as I said, there's the 2 main defining characteristics of LCDs will be what backlight type they use. And that's because they're always backlit, and we'll talk about what that means, as well as what actual type of LCD that they use. So the fundamental type, if each one can go between, so for something like a TN, TN being twisted pneumatic, but we'll get to those types later on, you can change the crystal's alignment. Now, we can make use of this through combining a couple of other technologies. For example, polarization of light. You might have heard that if you have light that is horizontally polarized, and polarization is a completely other topic that we'd need a couple hours to explain. So I'm not going to talk about that in this video. But if we have polarized light, and essentially if we have a horizontal polarization filter, that light will be allowed to pass through. If this is vertical, if we have rays of light, polarization is essentially which way the wave is going. You can choose to basically allow that light to go through, which means that this essentially looks like it is transparent and you will get the full image on the output. Or we can choose to give it the opposite orientation, which will essentially turn the pixel opaque and will not let any light pass through. So by combining this principle of polarization, by changing the orientation of these crystals, we can allow light to pass through or not pass through. And essentially, well, the LCD itself isn't the one allowing light to pass through. The LCD is just the thing that chooses its orientation. So if we look at the side view, and we have a plane of liquid crystals, which make it a little bit bigger. So say this is the panel of actual liquid crystals. In front of this, you will have a polarization filter. That polarization filter is essentially doing what I've described here, where if the polarization filter combined with the orientation of the crystals in the LCD, it will either allow light to pass through or will not allow light to pass through. Now, of course, if I had a black plastic cabinet at the back of this, that doesn't do us much good because then, well, you'd be going between, yeah, translucent and opaque, but there's nothing to see. So what we then do is behind this, we then use a form of backlighting. So backlighting will essentially produce the photons that are required for the LCD. In a really simple example, you won't have a backlight. For something like a calculator, you'll just have a reflective surface on the back such that the light of the room you're in will go through and bounce back. And that's why you won't be able to see them in the dark, but that's why you will be able to get shades of gray out of them by essentially blocking how much of the room's light is reflected back. For a modern LCD, though, this can be as simple as an incandescent light bulb, although that would be a terrible backlight, and we'll talk about why later. But you would get very dim blues out of something like that, and you would get way too much red and green. But for a long time, backlights were typically fluorescent. So think about the fluorescent tubes that are in this lecture hall. Take that, instead of using it to light a room, put it in a plastic cabinet, and put an LCD in front of it so that the light could shine through. That's basically what it was, a light with LCD with a polarization filter. And that way, essentially, when the crystals are oriented the light way and the panel turns transparent or translucent, you'll be able to see the backlight coming through. However, when the pixels then rotate, become opaque, you will see that as black because most of the light from the backlight will not be making it to you. Now, that would give you a black and white display. by using some colors along with those crystals inside the gel, we can then provide colors to this. So if you then take the red pixels and you allow light to pass through those, well, then the white light from the backlight is getting colored red because those pixels are allowing light to pass through. And if the green and blue subpixels are not allowing light to pass through, they're being opaque, then you would see that as a red image. Similarly, if you have if they're allowing blue light to pass through, but you're blocking the red and the green, you will see that as a blue image. And of course, by combining that for each individual pixel, we can get typically 16.8 million colors that you see today. And of course, that's because we're not just stuck with fully allowing light or blocking light. These days, we can run these with either pulse width modulation or through DC voltages so that you can essentially change what brightness, how much of that particular color can pass through. And why RGB? Well, that's something for a completely separate video related to how human eyes see and whatnot and psychology. So that's backlights, LCD, and polarization filters and how those work. Now, as I said, the two main things that distinguish LCD displays, and again, these are the most common types of displays that you see on the market today, are the backlight type and the LCD type. So let's start with backlight. The two main types of backlights that you will see will be fluorescent and LED. So that would be either CCFL or LED. And of course, that's because when LCDs were first being introduced, LED technology wasn't advanced enough to make them small and compact and efficient enough to run the whole display. So essentially, CCFLs are very much like the fluorescent you'd see, except the CC means that they're cold cathode. So whereas a typical fluorescent lamp would have two incandescent coils at the ends acting as a hot cathode, so when you turn it on, the two ends will heat up, essentially release enough ions into it until the thing can arc and then start producing light. CCFLs don't need those end coils. This allows them to be a lot thinner, which is what has allowed them to be put into like thin laptops. And it also means that you can turn them on and off without burning out the cathodes every time you do it. So, of course, CCFLs require high voltages, which means that for LCDs using this backlight type, they also need inverters. Because your DC 12 volts or whatever you're feeding in will need to get bumped up to thousands of volts AC in order to run these. This is, again, unlike hot cathode fluorescent tubes where you would be running them at relatively low voltages. But this means that you will need to run a DC source up to a higher voltage AC source. Whereas with LEDs, of course, being diodes, they can run purely on DC power. In fact, you probably won't even be giving it the full 12 volts. You will be using buck converters in order to lower the voltage that you're feeding it. But regardless of which type of backlight you're using, the principle is the same. We have some amount of light, and we're either allowing it to pass through or not allowing it to pass through colored filters. Now, next, I would just like to point out that so this is where the marketing sometimes tends to get confusing versus the actual technology. If you're looking historically from, say, 2000s to 2010, an LCD display always meant you were getting a CCFL backlight because that was the only backlight type, essentially, that was available to manufacturers and engineers. So you really didn't have a choice. It wasn't really all that confusing. You were choosing between CRTs and LCDs. Around 2010 or so, they started introducing what they called LED displays. Now, that might sound confusing because when you see LED, you might think, oh, the word LED is actually here, like with OLED. But that's actually completely wrong. LED displays are not OLED, and they're not actually self-emissive. So if you look at how LEDs work, LEDs can be as simple as pure red, pure green, pure blue, depending on which phosphor you're using, or white light coming from a foam flashlight, or the light on above the whiteboards. We see them in use everywhere these days. Hearing of an LED display, you might be inclined to think that how that should work is that if I have red, green, and blue LEDs, well, you might think that it's the LEDs that will light up to produce the image that you see on the monitor. But that's simply not the case. With an LED display, even if it has LED in the name, what you're actually getting is an LED backlight. What that means is you still have an LCD. They're not a separate display type. It is still the same fundamental principle, LCD polarization filter. The only thing that's changing is instead of using fluorescent tubes in order to light the liquid crystals, we're now using LEDs. So think like LED strips, basically put that along a pane of glass in order to diffuse it, and that's how LED displays work. Very much same fundamental. Again, this is something that has been very confusing in marketing over the years, but it's the same fundamental technology, just instead of using fluorescents, we're using LEDs in order to provide a backlighting source.
Thank you so much for watching part 1 of my Monitors and Displays 101 series. Part 2 and part 3 are linked in the description down below. If you enjoyed this video, please consider leaving a like or subscribing to my channel. I'll see you in part 2. Thanks.